Hello everyone, and in this lecture we're going to introduce the concept of union of sets, intersection of sets, different of sets, and eventually we will prove the commutative property of union and intersection of sets. Imagine of having two sets. The first set is A, composed by the elements 1 and 2, and the second set is B, composed by the element 3 and 4. If we want to merge these sets, we have a new set C composed by both the element of A and B. So it's composed by 1, 2, 3, and 4. The operation that we have done now is called union of sets and is denoted by A union B is equal to the new set C. In general, if we have two sets X and Y, we say that X union Y, and it's denoted by this notation if, results in a new set Z composed by all elements that are in X but not in Y, all the elements that are in Y but are not in X, and all the elements contained in both X and Y. Meaning that if Z is an element of capital Z, here, the first statement corresponds to the fact that Z belongs to X, but Z does not belong to Y. The second corresponds to Z does not belong to X, but Z belongs to Y. And the third is that Z belongs to X and Z belongs to Y. So let's do another example. We have the set L, which is composed by 1, 2, and 3, and the set M, whose elements are 3, 4, and 5. So our interest is to find the new set, which is the union of L and M. So we have 1 and 2, which are the elements belonging only to L. So 1 and 2 belongs to L, but not to M. 4 and 5 are the elements belonging to M, but not to L. Eventually, 3 is the element belonging to L and belonging to M. So, is the element that belong in both L and M. So, the union of these two sets is equal to, by definition, all elements in X but not in Y, where X here is L and Y is M. So, all elements in L but not M, 1 and 2. All elements in M but not in L, meaning 4 and 5. And the elements contained in M and L, which is 3 in this case. Suppose now that we want to take all the elements in both L and M, and we are interested in a set that satisfies only this property. So we want a new set whose elements are those contained in both L and M, and this is the only property that we want to satisfy. This new set that we can call by F, for example, is composed by the only elements 3. This operation is called intersection. In general, if we have X and Y, the new set Z, which is equal to X intersection Y, so the symbol is called intersection, is the set whose elements are all the elements in both X and Y. Meaning that for a generic element Z, this must be included in X, and also that Z must be included in Y, and both these conditions must be satisfied. Graphically, this means that if we have a set X and Y, we will take all the elements that they have in common. We can rearrange the graph of L and M in this way, and we see that the only element that they have in common is the element 3. So this is L intersection M is equal to the new set whose only elements is 3. Now let's go back to the example of before, the initial one, where we have the set A composed by 1 and 2 and the set B composed by 3 and 4. And we have said previously that A union B is equal to all the elements 1, 2, 3, and 4. But if we want to do the intersection, so A intersected B, we see that there are no elements that belongs to both A and B, so that the intersection is the empty set. If this happens, we say that A and B are disjoint. The last operation that we introduced today is the difference of sets. And so if we have two sets x and y, then x difference with y is equal to z, such that z belongs to x, but z does not belong to y. If we take the example of before, where we have L and M, so L is composed by the elements 1, 2, and 3, and M is composed by the elements 3, 4, and 5. If we want to write L minus M, we know that are all the elements belonging to L, but not in M. So it means that we have 1, 2, but 3 belongs to both, and so is not included in this difference of sets. If we have M minus L, are all the elements contained in M, but not in both. So here the elements are 4 and 5, and the elements 3 compare in both sets, so we're not going to include it. Another important property of union and intersection of sets is the commutative property, which states that A union B is equal to B union A, and A intersection B is equal to B intersection A. So it means that the order does not matter. So let's prove this property. The first proof is that A union B is equal to B union A. We can call X equal to A union B, so the new set X is the union of A and B in this order, and the set Y is the union of B and A in this order, meaning that we have to prove that X is equal to Y. In the lecture Introduction to Set Theory, we have shown that X is equal to Y if and only if X is a subset of Y and Y is a subset of X. So if we prove those, we have proved that A union B is equal to B union A. If a general element Z1 belongs to X, it follows that Z1 belongs to A but not B, Z1 belongs to B but not A, or Z1 belongs to A and B, because saying that Z1 belongs to X is the same as saying that Z1 belongs to A union B in this order. But these are the same condition for B union A. Hence, Z1 belongs to B union A, and so Z1 belongs to Y, which leads to the conclusion that X belongs to Y, because for each Z1 belonging to X, and we have proved that before, Z1 belongs also to Y, which is the same statement of this thing here. Following the same reasoning, then if a general element Z2 belongs to Y, it means that Z2 belongs to A but not B, to B but not A, or to both A and B, which is the same condition of, in this case, A union B. Hence, Z2 belongs to A union B, and it means that belongs to X, proving that Y is a subset of X, because for each Z2 belonging to Y, Z2 will belong also to X. In this way, we have proved the first property here, so that A equal B union B is equal to B union A, and now we need to prove that A intersection B is equal to B intersection A. The reasoning is quite similar to the one of the union. In fact, we have also Z1 and Z2. We call X equal to A intersection B and Y equal to B intersection A, so that if a general Z1 element z1 belongs to x, it means that z1 belongs also to intersection of a and b, which translates to z1 is an element of both a and b, which is the same condition for b intersection a, meaning that z1 belongs to b intersection a, and hence z1 belongs to y. This proves that for each element z1 belonging to the set x, then z1 belongs also to y, and x then is a subset of y. The contrary is the same reasoning, so z2 belongs to y is the same as saying that z2 belongs to b intersection a, but it's the same condition as before, so z1 belongs to both b and a is the same condition as z2 belongs to both a and b, which means that z2 belongs to x, and in this way we have proven that for each z2 belonging to y, z2 belongs also to x, so y is a subset of x. These two together proves that x is equal to y eventually. And so we have proven the commutativity of the intersection. Thank you for watching. If you have missed some lectures, you can go on my channel, and remember to subscribe if you liked this video. See you!